Okay, so last time we did more properties of posets, which is defining what is partial order in contrast to equivalence relation, how to represent partial order using a diagram, and then these substructures inside partial order called chains, respectively anti-chains. So longest chain is actually very short, it's only n plus 1, while the longest anti-chain happens to be extremely large, right? You can just take all n choose n by 2 subsets of size n by 2, and that is very close to 2 raised to n. So there is this old theorem that we will prove. Sperner's theorem says that longest anti-chain is only of this type. Any questions till now? There was also a tutorial, I think, on Saturday. Was that fine? Some people say no, but well, you can't get everything. Okay, so let's continue with this proof. Although it's a very old proof, it's not easy. It's elementary and tricky. So we want to show that the longest anti-chain of a poset of size n is, well, I should also say that it's not a general poset, right? We are looking at this very specific poset where the set is the collection of all subsets. So it's the power set, and less than equal to is containment of subsets. Right? We have fixed this poset, and for this, so in the poset there are these 2 raised to n elements, basically all subsets, and let's take a maximal chain, which we call in short M chain. So we have counted this. This is always n factorial, because you can, no matter what these sets S0, S1, S2 dot Sn minus 1 are, they are in bijection with total order on the elements, which is 1 to n. So the number of ways you can fix them is the number of permutations, number of orders, that's n factorial. So chains or M chains are well understood, completely understood. Anti-chain is the mystery, right? So let A be an anti-chain. What we will do is we will use chains to deduce properties about anti-chains. Okay, so let's fix the anti-chain to be A, which ultimately we will assume is largest possible. But for now, we don't need that assumption. What we can show always is that any chain will intersect with the anti-chain in at most one subset. Because if it intersects in 2 subsets, yeah, then the chain has a relationship between the 2 subsets, which will transport to anti-chain, and that will be a contradiction. Right? So anti-chain can only cover one subset or one element per chain and not more. So then we now need to count how many chains are there containing one element, which in this case will be a set S of size k. So we fix the set S and we count the number of M chains that will contain this. So note that by the size, already its position in the chain is fixed, right? Where S will sit, that is already fixed by the size. So it has to be in this place, which is kind of the kth location, and now the subsets and the supersets are what are free, and they are again as used before, they are again in bijection with the order of the underlying elements. But I mean the set of elements is fixed, right? It is fixed by S. And similarly in the superset, the elements which are outside S, they are also fixed, they are n minus k many. So only thing which you can vary is order. So for the subsets, the order you can vary in k factorial ways, and for the superset part, I mean elements outside S complement, that you can vary, you can order in n minus k factorial, so you have the product by the product rule. Okay, so the count of chains or maximal chains containing your favorite set S is this, which as an exercise you can show that it's at least n by 2 factorial square, or if n by 2 is not a number, then you take floor and ceiling. Is that fine? So how these things will be useful, that will now we come to the tricky part. So if this part is not clear, then you should ask, because later on things get more complicated. So now let us look at all the M chains. So let's give them names. So first is C1, second chain is C2, and we know that there are n factorial many chains, right? So let's number them like this: C1, C2, Cn factorial, and your anti-chain is A, which is a collection of subsets, right? So let's call the subsets S1, S2, and S sub A. So what we have shown till now, let's apply it here. So this first element of the anti-chain, this set S1, how many chains will contain it? Maximum how many chains can contain this? We are interested in that number. So let's call that S. Let me do it slightly differently. So we have shown that S1 and S2, they cannot appear together in any of the chains, right? Or in other words, S1 will appear, if S1 appears in some chain Ci, then no other set can appear in Ci, right? So this means that what will happen is S1 will, if it appears in some of the chains, then S2 can appear only in other ones. So S2 can appear, say, in these, and S3 can appear in the next, and SA can appear in some of these. So the places where they appear, these M chains are disjoint, right? So now can you deduce the number of chains in which S1 can appear, like a bound? So something like n factorial by a. Right, intuitively, any of these anti-chain elements, they can appear in around, by averaging around n factorial by a, but we have to make this formal because some may appear more and some may appear less and some may not appear. Actually, can it happen that an SI doesn't appear in any of the M chains? Right, because any set you take, like we did in the one of the blue properties, we took this set S and we counted how many M chains there are. So there are always M chains for any set. So each of these SIs, they actually have corresponding chains where they appear. So which means that if you look at this, the green parts that I have drawn, they partition these CIs, and also all the CIs are covered. Okay, it's actually what it is doing, it's inducing a partition. That is what we want to use. So let me make the following claim, then we'll prove it. For all I, Si appears in greater than equal to n factorial divided by n choose n by 2 chains. Okay, I am making this claim here that the sets which you have in the anti-chain, you pick any set, the green parts which I have drawn, whichever one corresponds to S1, it is of size at least n factorial divided by n choose n by 2. Can you prove this? Yeah, this is actually this part is the same as the above blue part, right? Because what is n factorial, what is n choose n by 2? It is n factorial divided by n by 2 factorial times n by 2 factorial, floor ceiling. So you simplify it, you get the same expression, lower bound, that was left as an exercise. So that we have already shown, right? We have just changed the form of that expression, it's the same value. So now you have information about the size of these green braces, and from that you can deduce how many parts are there. So how many parts you deduce? Yeah, so you deduce that so number of green parts. See, since you have a lower bound on each on each green part size, you get an upper bound on how many parts there will be, right? The opposite. So number of green parts has to be less than equal to total number of chains divided by this expression. So let's call this something. Let's call it m. So n factorial by m, which is n choose n by 2. Okay, and so this is on one hand. On the other hand, number of green parts is just a, right? Because they actually are in. These parts are in, they are defined by SIs and they are all disjoint. So this on the other hand is actually by definition A. So what we have deduced is that the size of an anti-chain is always less than equal to n choose n by 2. Is that good? Yes. The whole thing since the beginning of time. So did you understand how these green parts were created? So then the number of green parts is then A, right? You understood that. Now let us try to show that each green part is large. Okay, so how large? We show that each green part is at least m large, right? Where m is this expression we got from the exercise. Because basically it holds for every k, and if you take S1 for example, whatever is its size, let's call it K1, for that m will be a lower bound. The size of S2 if it's K2, for that also m will be a lower bound and so on. So it's a lower bound for every green part. So once you show that each of the parts they are large, then that is it. So then you get that the number of green parts cannot be too many. Yes. Yeah, that is actually, we have said something much more. Look at the number of m chains with S. It's not only that for every set there is a chain, there are many m chains. We already showed that. No, you take some Si, there is at least one m chain. So there is a green part which is non-empty. They have all the CIs will be covered. Okay, I see what you mean. Yeah, maybe it's not. No, maybe not everything is covered. That's possible. But will that change the argument? Mm-hmm. Okay. Yes, but still maybe the last C n factorial is missing. That's possible. But it's okay. So what you will get is still here in the number of green parts calculation, the n factorial that I'm getting, you will get something smaller like n factorial minus 1. So that is fine. So all the claims are correct. Yeah, so I should not say like a partition, but a partition which will covers let's say most of these m chains, if not all. But the number of m chains you know is n factorial. So whatever you cover, it's less than equal to n factorial. You have shown that each green part is large. I mean, it is at least m large. So you get n factorial by m as the count, which is now a is less than equal to that. Yes. No. So A is just it is just size of the set, right? That's the definition of A. Right now, don't worry about maximum or minimum. This inequality holds that size of the anti-chain equals number of green parts, and number of green parts is less than equal to the chains that it covers divided by the lower bound m. So this slide is correct. Now what's the question? Yeah, so those will need separate proofs, but I don't need it right now. So right now we just stop here. That we have what we have shown, just read it, that the size of any anti-chain is always below or at most n choose n by 2. Is that clear? Hence, the largest anti-chain is of this size, and you also know it. You know one example, so you know that this is correct. I mean, this is optimal. It can be achieved, and nothing better can be done. But remember that Sperner's theorem wanted or claimed more, right? This actually claims that yeah, there are only one or two examples of longest anti-chains. So now we have to prove that. But our machinery is now set, so we'll just use these tools more. So let us first note that the above proof shows to now the question of maximizing the anti-chain, right, as she was saying. So let us, when we think about a longest anti-chain, to get largest sized anti-chain, for all I, these the subsets that it has, they can only be either k or k plus 1, where k is this expression n by 2 floor. Do you see this? Is there anybody who does not see this from what we just did? That when you are interested in maximizing your anti-chain, then every set that it has, the size possibilities are only 2. I mean, it will be 2 if n is odd. If n is even, there is just yeah, this needs a change, I guess. Sorry? Yeah, so but then there is a problem in the way I've written it, right? I want to say something stronger. So n by 2 or so this is, let's say, k, and this is k prime. Let me use this. So the above proof shows that the sizes of the sets or the sets in the anti-chain, their size possibilities are only 1 or 2. It's basically this around n by 2. Do you see why? What's the how do you get this? Right. Yeah, so you basically you go back from the last property, you reverse engineer. So you say that, okay, I want A to be maximized, which means I want its size to be n choose this thing, n choose k. You want not less than equal to, but exactly equal. So now from this exact equal, then you have to get number of green parts to be exactly equal to n choose k, and which means that now again you move back to this last blue property, that Si has to appear in exactly m, not greater than equal to m. So now you know the green part size exactly. It has to be exactly this thing, n factorial or this k factorial times n minus k factorial. So that the blue property above, there also you have to have an equality, which means K has only two possibilities. K can only be floor n by 2 or ceiling n by 2. Okay, so you can go back, just follow these equalities. So make each less than equal to 2 equal to in the above calculations. Okay, so that will give you the, and K, remember, is the size of the set S, right? So for every SI you actually get the size information. So when n is even, all of them are size n by 2. In which case we are done. The Sperner's theorem is proved, because you just, that was the whole example, that you take all n by 2 size subsets. So for even it is done actually. So theorem is already done for even n. So from now on, what we will be struggling with is odd n, right? Because in odd n, the sets can be of two sizes, either n minus 1 by 2 or n plus 1 by 2. So in the case of 101, it can be 50 or 51. So maybe we write that down. So odd n means that for all I, your SI is either size k or k plus 1. K plus 1 is basically k prime above. So it is conceivable that instead of taking all k size subsets, you take some of them and you take some subsets of size k plus 1. That may also give a longest anti-chain, right? But Sperner theorem claims that it will not be possible. So why is that? What do you do now? So what we do now is prove this interesting lemma that if your anti-chain is the longest, if a longest anti-chain A contains an SI of size k, then it contains all. Then it contains all subsets of size k. Is it clear that if we prove this lemma, then Sperner's theorem is proved for odd case, right? Because there will be two possibilities, right? Either your longest anti-chain contains some set k subset, in which case it will contain all. So that was the classical example we gave. Or it doesn't contain any subset of size k, in which case it contains what? It is forced to contain all subsets of size k plus 1. Right? So there are only two possible anti-chains. Once we show this lemma, is everything. So how do you show this? So we show this through an intricate proof, again using the things that we have developed till now. So let S be the subset we are looking at. And the natural thing, I mean the direct proof will be that from this S, see you want to show that some other K subset S prime is also in the anti-chain. So you try to deduce that from S I can go to S prime and show it in the anti-chain. Okay, so that is what we will try to do. We will try to show that any S prime that we think of, S can help us take us to S prime within the anti-chain, hence showing that every K subset is in the anti-chain. So let S prime be some K subset not in I think I don't need to say not, maybe I don't give a proof by contradiction, let's just go directly. So let S prime be some other K subset, and what we will set up is this process where okay, let's see an example first. So suppose you have subset 1, 2 and you want to go from 1, 2 to 3, 4, right. So what you can do is you can delete 2 and append 4, right, and then delete 1 and append 3, right. So you can do these 4 transactions. So from this you can go to 1, 3, and from this you can go to 3, 4. Or actually I want to, maybe I want to go to a bigger set. So let me introduce, first I append 4, then I delete 2, next I append what? 3, and I delete 1. Okay, so that is what I will now do formally. So if from a 2 subset, let's say 1, 2, you want it to go to 2 subset 3, 4, then these are the steps you can take. You can make the set bigger, then make it smaller, then bigger, then smaller, right. So that is what we will do to get from S to S prime. So from S we will, S we call S0, we go to T1 which is bigger, then we shrink it back, call it S1, then we go to bigger T2, shrink it back, so on. Let's say we reach TL, and then we shrink it back to SL, that will be S prime. Okay, so here are the sizes. So size of S0 is, we started with K, right? Then we go to K plus 1, then we go back to K. That's the process. So we know that S is in, I mean this sequence, we know we have only one information, that S is in the anti-chain. Can we make any statement about T1 being in the anti-chain or not? Is it there or not? It cannot be, right, because S and T1 are related. S is smaller than T1, so Since we know S is in the anti-chain, T1 cannot be. It's not in the anti-chain. Now, since you know that T1 is not in the anti-chain, what can you say about S1? Yeah, so now comes something that I think a student was saying before. She was saying that since A is a longest anti-chain, it should have something from every M chain. So we will not now use that idea. So the question you ask is after T1 S1, is S1 is in the anti-chain? So the answer will be yes, because you consider the M chain that has T1, S1, and we don't care what below or what above. So consider some anti-chain which has this T1 containing S1 thing, and then after S1 you have subsets, before T1 you have supersets. Do you agree that from this M chain something has to be there in the longest anti-chain A that we have? What is the reason? Sorry? Yes, that we have assumed, but why should it have something from every M chain? Yes, so that's what I'm claiming. So convince yourselves that that is true. And since now for this M chain, I have not even fixed the dots, right? Dots can be arbitrary. And all I know is that T1 is not in the anti-chain. Can you deduce that hence S1 is in the anti-chain? How do you deduce that? Since T1 is not in the anti-chain, hence S1 is. Why is that? Well, this is easy to see because in the whatever the M chain is, there are only two elements in this chain, M chain, which have the correct size, k or k plus 1. Right? So T1 has size k plus 1, that is ruled out. So the other one which has k size, S1, that is forced to be in the anti-chain. Okay, so S1 is in A then. Is that clear? You are asking why should every M chain have some element in A then? No, that is what we agreed from that side of the class. That every M chain has some element present in the longest anti-chain A. Otherwise, it won't be longest. So assuming that this M chain also has to contribute something, it cannot contribute T1, so it is forced to contribute S1. And what do you do after this? After this, you repeat. Right now, you do the same argument. For like we went from S0 to S1, now you go from S1 to S2. So repeat this. So now when you repeat, you will now get next you will get S2 is in A, then you will get S3 is in A, and if you wait for a very long time, then you will get SL also in A, right? Which means that whatever subset you want, you can put in the you can show it to be present in the anti-chain. That was the lemma. So this means that every K subset is in the anti-chain A. Is that clear? Any questions? So you go home and read this again. This proof is full of tricks. And right, so since we have the proof of the lemma, we have finished the theorem. So this now means that when n is odd, in that case this longest anti-chain A, it is either all the K subsets or it is all the K plus 1 subsets. Okay, by this we will always mean that yeah, this is just all the K subsets. That's the notation. Set of all. And this is set of all K plus 1. Okay, so for odd there are two possibilities, and for even there is just one. Okay, that is Stirner's theorem for longest anti-chain. Any questions? Yes, so even posets have great properties, very non-trivial to prove. There are more properties, but we will not go into the details of those proofs. So let me just state them. So the key idea here was this relationship between chains and anti-chains. Right, that is what we used. There are much stronger relationships that we can prove. So first is what is called Mirsky's theorem. This is from 71. So this says that if the longest chain in a poset has length r, so this is yeah, I believe this is now for a general poset, so we don't need to think about the subsets, the power set example. In general, for a poset, if longest chain is length r, then you can partition the poset into r anti-chains. Okay. So if the longest chain has length r, like in the power set case, longest chain had length, length n plus 1. So what this theorem is saying is that you can partition the power set into n plus 1 anti-chains. Do you know what this decomposition is explicitly? Yeah. So it's the same that we discussed, right? You take first anti-chain you take to be 0 subsets, second you take 1 subsets, 2 subsets, n by 2 subsets dot n subsets. Okay, so that's the classical example we started with for power set poset. But one can prove this, I suppose, for any poset. That is Mirsky's theorem. So longest chain and the chains and the anti-chains are very strongly related. And the other theorem is the dual of this, so longest anti-chain versus partition into chains. That is by Dilworth. So if the longest anti-chain has length r, then the poset has a partition into R chains. Okay, are the statements clear? If the statements are clear, then you should also see that they are intuitive. Okay, you want to partition the poset into disjoint chains. So if you, in a way, if you picked specific elements from these parts, you should get an anti-chain which is longest. Okay, so it shows the duality between chain and anti-chain in a very exact way. Any questions? Okay, no questions, then we will start a new topic, which is graph theory. So graph theory also started like anything in combinatorics, just a set of puzzles and curious results. But within 100 years, it became a very serious topic of study, and in computer science, many of these things are used in algorithms and in modeling problems. So we will, of course, not be able to do difficult things in graph theory, but we'll only do basics in this course. So let's start with some basic graph theory. So graphs are usually very natural to model real life problems. to model connections between objects. So for example, I mean just in the problem definition, you will see that graphs appear in communication networks. Social networks, and anywhere, for example, in transportation, and so on. And of course, when they appear in these examples, the graphs have different properties, even different definitions. So we'll start with the most basic one, which is the following. So graph for us, unless said otherwise, is a tuple of two sets. First is called vertices, second is called edges, vertex set, edge set. Has vertices V and edges E. The condition being that if u comma v, so okay, I mean when we say edge, it is clear that these elements will be pairs of vertices, right? That's already inbuilt in the term, but I can add it here. So E will be some subset of V square. Such that if u comma v is in the edge set, u comma v means that u is connected to v. Or V is adjacent to U. Okay, so these terms I am defining here in one go. So graph is this, vertices is the first set, edges is the second set. Something being present, pair u comma v being present in E means that in words we say that V is adjacent to U or V is connected, U is connected to V or V is connected to U. Sometimes the order is actually important. So U is connected to V, I want to draw the arrow from U to V. We will sometimes also use V of G or E of G. That will just mean that give me the vertex set of a graph and give me the edge set of the graph. So there can be graphs of this type. This can be a graph, vertices 1, 2, 3, right? Or it may be like this. So when there is a self loop, or when there is no self loop, we call the graph simple. Okay, and when there is a self loop, we call the graph non-simple. And you can see that I am not drawing arrows here, which means that 1, 2 is in the H set. What about 2, 1? That is also in the H set, right? So if I don't draw arrows, then it means that it is bidirectional edges, which is called undirected graph. Else it's called a directed graph. So that facility is already there in the definition. You may choose to have only 1, 2 in the H set, but not 2, 1. Then you have to draw arrows. If both of them are there, then you don't need to draw arrows because symmetric relationship. Okay, so that is simple. Graph G is simple. If there is no loop. That is u comma u is never in it. No, none of the u comma u's belong to the H set. Okay, so simple properties. Simple graph has how many edges? Simple graph on n vertices, let's say. So number of edges can be 0, but what is the maximum number of edges? NC2. I mean, if you have arrows, then yeah, so it can be n times n minus 1, right? Or NC2 if undirected. So the point is that in terms of vertices, which is n, the number of edges in all the cases is around n square. It's never more than n square. So that is the size to represent a graph, right? You need this n square amount of information. Okay. Yeah, but it may also happen, you may sometimes have, but we will not use it probably. You may have multiple edges between vertices. Don't need it here. Let's write it down. If two vertices have multiple edges, then the graph is not called a graph, it's called a multigraph. Is there a practical situation where you will need two edges between vertices? Yeah, even in transportation it can happen that between two important cities you have two roads, multiple roads, right? So that will need a slightly different picture. There may be, for example, things like this happening. But we don't want to study this immediately, so we will not study multigraphs, we will just assume. I mean, once you allow multiple edges between two vertices, now the number of edges can be anything. Now it's independent of n, nothing to do with vertices, right? So we will not use these for now. This modeling can also be done. And yeah, directed, undirected is just this. If the edges have directions, then you call it a directed graph. If edges in both directions, then you call it undirected. Edges may also have weights on them. So for example, you may have weight, I mean if the example is of roads, then the distance is a weight. That's very common. So you may have weight 10 here and weight 2 here and 3 here, and there may even be negative weights. Weights can be anything, so you may have a real weight. Right? So these graphs are then called weighted graphs. And usually if there is no weight on the edge, then you assume the weight to be 1. So there is a lot of qualifiers here. You may have to say G is a undirected, unweighted, simple graph, right? And then any possible combinations of this will also be valid. But when we don't say anything, we just mean simple, unweighted, undirected. That's a graph. Usually we'll work with those. Oh, time is up. Okay, you can ask questions.